Thank you very much. Thanks to the organizers for having me. For my own benefit and for the benefit of the organizers, I'd like to point out that the kind invitation to speak preceded Q-CTRL's offer to host anything and sponsor the event. This is not pay for play, and we're very proud of that. I wanted to give a talk today that, as Andrew says, is beyond just quantum error correction codes. I will do my best to make the links clear, because what we're interested in is this interface between what we might call physical layer control or virtual layer control and quantum error correction. I'm going to try to give a reasonably high-level talk that threads the needle of the different backgrounds in the audience. Most of the work I'll talk about comes from my academic team at the University of Sydney, where I'm part of the Center for Engineered Quantum Systems, but of course also feeds into the things going on at Q-CTRL. I wanted to spend just like a minute with one slide to introduce Q-CTRL. For those of you who don't know, we are a company that focuses on infrastructure software for quantum computing, where the focus is on quantum control engineering, trying to extract useful work from quantum devices. And our inspiration really comes from this tremendous history that control engineering has in classical technology. You can look back to the dawn of flight and the Wright brothers. And if you look at what their fundamental contributions to the field were, they were things like three-axis control, roll, pitch, and yaw, things that stay with us today. And you can play that tape forward in all sorts of other technologies like drones and quadcopters or walking robots or autonomous vehicles. It's been control that's been a key enabler, and Q-CTRL as a venture capital-backed organization is focused on building tools that help the broad community, from hardware manufacturers all the way up to programmers. That's it. That's enough sales. At this point, I wanted to introduce the technical topic that I'll be focusing on today. It really comes from this chart that I think most people in the room are familiar with from Cody Jones et al. in 2012, looking at this so-called layered architecture of how one designs the software stack for a quantum computer. And I want to talk really at these bottom layers, the physical, virtual, and quantum error correction layers. And I'll tell you more about what I mean by these in just a couple of minutes. But after a little bit of background of what it is that we want to talk about, I'll share a bunch of experiments that look at the interface between these low-level control solutions and quantum error correction in the kind of more canonical sense, where we look at the role of these procedures in suppressing errors deterministically, and that's important because it's not some kind of like randomization scheme where you have to do many repetitions of the same circuit. It just is a drop-in kind of replacement for standard quantum logic. The ability to homogenize errors in space and time. I'll tell you a little bit more what I mean by that. And then the bulk of the talk will focus on some experiments we did looking at how error correlations are modified by quantum control, and then I'll just give a little bit of an outlook. I want to emphasize that my academic team is an experimental team, and so throughout this talk I'll be showing experimental data, and it's all derived from our preferred platform, which is trapped atomic ions. I'm not going to talk more about this. Suffice to say that there's a qubit. The qubit is in the satellite communications band, your 12.6 gigahertz. You can control it with microwaves. You can do all sorts of standard laser entangling gates and the like. If anybody wants to know more about that, please feel free to ask me. You'll hear more about it from Jonathan Holm tomorrow as well, and maybe from Ken Brown's team. But I wanted to come back to this point that Isaac made in his talk to remind us all why we're here. Right? Now, everybody knows why you're here. I know you know this. But sometimes I think it's useful to turn units from different communities into a comparable form. And here are two different ways to look at it. There's a lot of work looking at what is the likelihood of hardware failure in classical microelectronics. These numbers vary quite a lot by application, but the failure rate, which is not measured in the way we measure it in kind of quantum error correction land, is usually measured in units of what are called failures in time. Failures in time are the number of failures in a billion hours of continuous operation, right? And so the numbers turn out that the probability of failure of an individual kind of logic gate, one operation occurring in a clock cycle on a single transistor, is something like 10 to the minus 24 to 10 to the minus 27, right? And so that means that a single transistor in your computer can run for about 1 billion years continuously at a gigahertz before it's likely to suffer a hardware fault. And we all know what the story is in quantum computers, and obviously this enormous difference you can think of as almost an Achilles heel, and this is why we're all so interested in the variety of strategies that one can take in order to tackle this problem. So if we come back to now just the Q-control stylized version of Cody's chart, we focus primarily on this low level of the stack that for our purposes we call quantum firmware. These are things that we like to abstract away from the higher level users. We don't expect that anybody running an algorithm is going to know very much about the kind of specific time domain modulation protocol employed to implement a high fidelity Mulmer-Sørensen gate or something like that. There are a variety of tasks that one performs, characterizing noise in the system, doing classical feedback stabilization, and most importantly, error suppression. We lump that all together as quantum firmware. And in this layered architecture, we think of that as just the lowest layer of the stack. You improve the gates and the hardware, and then you go up to quantum error correction above it, and then compilation and logical encoding. I guess the argument that I want to make, and I hope it's not too unpopular, is that this is a fantastic paradigm when we think about quantum computer science, and we think about asymptotic proofs about what one can achieve with a quantum computer. But one might want to think about this a little bit differently in the context of quantum computer engineering, where really there's this blurring of the boundary that originally was drawn as quite distinct between quantum error correction and quantum error suppression, or these lower level quantum firmware protocols, right? And you can even imagine that other parts of this blend together, but I'm going to focus on the blending of these two elements. And really, from a kind of control engineer's perspective, although I'm a physicist who pretends to be a control engineer, I mean, you can see what the links are by taking the conventional approach to analyzing this problem. This is what a control engineer would draw. It's called a block diagram, and it's an extremely powerful tool in engineering because there's a whole bunch of math that can be abstracted into simple rules about the input X and the output Y, right? Now, the math used for conventional classical systems doesn't carry over very well. We do things a little bit differently, but broadly you have some quantum system here subject to a disturbance. In control engineering parlance, this is called the plant, and it can be acted on by a controller. What you see is that the conventional approach to stabilization that would have some measurement feedback, well, that's still present in the context of what we're discussing today. We know that projective measurement destroys quantum states, so we don't want to do that. But quantum error correction is really just a fancy form of feedback stabilization. In fact, it's not even fancy feedback stabilization, it's feedback stabilization with a fancy measurement model, right? Where you do indirect measurements of parity and things like that to do syndrome extraction. But ultimately, you're getting some information about the system and using that to actuate on the system. Now, what we do in quantum firmware is we focus primarily on this so-called forward branch or the open loop path, the part that doesn't have any measurement. And the important thing to note, apropos of what I was just saying, is that it's the same controller, right? It's the same kind of actuation you have on your devices, things like performing bit flips or phase flips or kind of generalized rotations in an open loop way that you do when you're performing quantum error correction. This is a shared resource. And so you already see that there is this kind of intersection between the two paths. So now I want to tell you about what are some of the benefits that come from attacking this problem of error in quantum computing at the lowest level, at this firmware level. I think the first one everybody is familiar with, and that's the idea that using these control solutions, sometimes known as dynamic error suppression or dynamic decoupling in a very specific instance, you can reduce the likelihood of error, right? If you have some unitary operator, which can be decomposed into the perfect unitary and then some error component of the unitary, you can use concepts like average Hamiltonian theory to generate the right manipulation of, say, a qubit in this simplified picture in order to enact the same logical operations you care about, like x's and z's and h's, however, doing so in a way that is robust against noise in your physical noise in your system, right? This is a well-trod path that's very familiar in, say, EPR or NMR literature, and obviously has been around for a long time in quantum computing. And the impact on quantum error correction is quite obvious, right? We're trying to get below the fault tolerance threshold, and not just below it, but as far below as we can in order to maximize resource efficiency. One important point that I want to make here is that these approaches are deterministic in a way, right? If you take your quantum logic operation and replace it with the dynamically protected version, the likelihood of error goes down. There's no repetition and averaging that's required. Of course, this is all in an ensemble average picture. So here's a trivial example of how you can see this in action. What we're looking at now is a control solution that's derived by a machine learning package. It happens to come from a Q-control product, but that's immaterial. What you can do is apply an error. You apply, in this case, quasi-static noise that happens to be here either an over-rotation error, like your Rabi rate is wrong, or the time of your pulse is wrong, or on the right for you, you have a detuning error. Your qubit is off resonance from its drive. In the middle, there's no error. As you move away, the error gets bigger on either side. And what you see is that with a conventional solution, which is just a pi pulse in this case, as you increase the magnitude of that error, the measured error, being in the probability of being in the wrong state, which is just a projective measurement on the qubit, goes up, but it stays low over a broad range of these induced error values when you use a solution that in this case is derived to both suppress dephasing errors and control errors, that is over-rotation errors, right? Now, this happens to be a cool one that you can do much faster than you can achieve the same operation using analytic approaches that come from the NMR literature. It's about 5 times faster. But this is just a totally trivial example of how you can build error robustness into your physical operations. It's maybe a little more fun when you think about doing this for multi-qubit entangling gates. How do you use control to suppress error? Well, to start with, how do you do gates in trapped ions? I think most people in the room may have at least heard of this, that what we employ are the quantum coherent modes of motion in the ion trap. So it's not just the internal states of the atom that we employ, it's also the oscillator modes, the bosonic modes. And you can kind of think of this as like Newton's cradle, that you have some marbles that have shared modes of motion. And it's through those shared coherent modes of motion that we can perform entangling operations. The most famous is called the Mulmer-Sørensen gate. And really, it's a reasonably simple thing. You drive your oscillator off resonance with a particular laser-induced force. And when you do that, you make some excursion in phase space. This is the oscillator position in momentum space, such that if you enclose a particular amount of phase, you end up with an entangling gate if you've applied it in the right basis, right? That's really simple. The idea is you make a loop in phase space. Using a state-dependent force, you end up with an entangling phase. I think what you can start to see is that if you've performed this gate and you've done it in a way that is maybe not quite correct, I lost a thing there. You see that you may not close that loop. If you don't close the loop, that means that you have some residual excitation of your oscillator, and that residual excitation, when you trace over it, leads to an error term in your Mulmer-Sørensen gate. And this is kind of the dominant source of error that we see in most cases. It comes from your trap being unstable and the frequencies drifting around. It comes from the laser amplitude being unstable. This is the big problem, and it gets much, much bigger as a problem when we think about not just a pair of ions with 2n transverse modes, say, or 3 times the number of ions, normal modes overall, but you have many, many modes. And the way this problem kind of can be interpreted is like, if anybody grew up in a place where you went to school on the school bus, on the rainy days, you remember like staring out the front windshield and you have the 2 oscillators, the windshield wipers that start in phase and over time they get randomized and they're doing crazy things. It's a little bit like that with these oscillator modes. You want to try to make sure they're synchronized and they close the loop at the same time, but they obviously have different frequencies. And this leads to circumstances where in order to make sure all the loops close, you face a challenging problem where you either have to wait long enough for, imagine not just 2 windshield wipers, but imagine a dozen of them, for them all to come back into sync, right? Well, waiting for that is generally prohibitive in terms of the penalty in time, and so we look at other ways to do this. And the other ways are, they take various forms. Our team prefers modulating the phase of the drive. Chris Monroe's team with Lu Ming Duan worked on amplitude modulation. Ken Brown's team worked on frequency modulation, which obviously is directly related to phase modulation. But the idea is that if you make this excursion in phase space, which is induced by some radio frequency source, we have a laser that's being modulated. If you advance the phase in the right way, you can ensure that all these different modes come back and close the loops. And by enforcing a particular symmetry constraint, you can ensure that it does this in a way that's actually robust against the dominant sources of noise. And so these gates are robust against laser amplitude noise, trap frequency noise, and even AC Stark shift. So your qubit just asymmetrically shaking, right? And it comes by not just doing a simple loop, but making these much more complicated epitrochoid-like patterns in phase space. And the summary here, this is really for the experts, is that if you want to drive as fast as you can, you want to make your gates as short as you can, there are only certain conditions in which you can nominally enforce this entangling phase condition in the standard way. That's the black data, where the fidelity goes all the way down to 50%, which means you're not doing a gate in certain cases. But we can achieve our maximum using these robust control solutions for effectively any laser setting. Right? For the experimentalist, that's cool because it gives you a lot of flexibility, but just the takeaway in general is that we can achieve better than 99% fidelity where we're limited by spam. So there's no subtraction of spam here. This is the actual overall measured value, and we know that about 0.5% at least is coming from spam. So these are a great kind of set of techniques that are really helpful. So the first point, quantum control allows you to do better gates. Lower likelihood of error, higher fidelity. The next part of the story is that when you use control solutions, you don't just say overall reduce the likelihood of error, you also homogenize the errors that are measured in your device in both space and time. Right? For those of you who come from an NMR or EPR background, this is a very, very familiar concept in composite pulse land. But if you just imagine some kind of cartoon device where you have a variation in errors, maybe you'll have your best performing qubit, which is the one that you report in your paper, but then there's the worst performing qubit, which is the one you try and hide. When you don't have quantum firmware, you just get this variability when you don't use control solutions. But if you make the celebratory choice to implement quantum firmware in your device, you overall homogenize the error rates, even in cases where the best performing qubit does not get better. And that's important because we always focus on that one. We say, well, if I measured 99.5%, did it go to 99.7%? Well, maybe it didn't, but maybe the one that was 90% went up to 99.5%. And so this is an idea where using quantum control can reduce the gap between the mean or median and the worst case errors, which obviously is relevant in the context of logical encoding. So here are data that are taken from a paper by Fred Chong's group looking at the IBM device, or one of the IBM devices with 16 qubits, where just looking at a bunch of different physical devices on this chip as a function of time and a bunch of different 2-qubit gates as a function of time, there's just this enormous variability in the device performance. Now, of course, we report the best, but the reality is that the coherence times range from 20 to 120 microseconds, and the errors on these 2-qubit gates, even for a single gate, will range from a few percent up to about 15% error. Right? These are very big variations. It's not uncommon. This is not a criticism of IBM. We see similar things across everybody's devices. Right? So this is the kind of thing that we want to think about in real hardware systems and what might be done about it using quantum control, for instance. One proxy measure that we're going to employ, and I'll use this throughout the rest of the talk, is randomized benchmarking. Right? So I think you're mostly familiar with this, where we're going to implement some random series of Clifford operations such that we, at the end, implement something that looks like the identity operator. And we're just going to say, how well did we do this as a function of how long our circuit is, how many operations we perform. And so the proxy measure is PRB, you can call it an error probability. It's like a return probability or survival probability in this generalized protocol. It's a measure of how well you're doing your individual gates. What we'll generally be doing in these experiments is taking each of those Cliffords and replacing them with their dynamically protected version, with their quantum firmware alternative, their cousin who is robust against error. Right? And you do the same experiment. So here's a really simple experiment where we're comparing randomized benchmarking, not the whole protocol, just one randomized benchmarking sequence, one potential randomization, where we do the standard version in black and we do the dynamically protected replacement version in red. And you just do it over and over and over again, for 8 hours in this case. And you see that we have this outrageous variability in our results when we use the so-called primitive gates, the standard implementation. And this is because our experimental systems drift, right? It's the calibration of the amplitude of the microwaves that has changed over time. And you see that even though you're suffering from exactly the same thing, because these experiments are interleaved, that by using the control solution, you homogenize the performance over this time window, right? And the kind of intercalibration time for most devices on the cloud is about, say, 6 hours, right? So this is a demonstration that control can homogenize gates in time. We can also see this in space. So here is an example where we have 5 ions in the trap. We perform parallel randomized benchmarking on each of the qubits. Now this is single qubit randomized benchmarking on each one with the microwave field. And we happen to have what we've measured is a microwave field inhomogeneity, which comes from like a standing wave pattern in our trap. And that leads to some small variation in the Rabi rates. And these are all variations for the experimentalists at like the Hertz level. These are very small changes. And then we measure the randomized benchmarking probability, PRB, which we want to be small. And we see that across these devices, in red, we have the primitive version of randomized benchmarking, and then in blue, the dynamically protected, the quantum firmware version in air quotes. And again, you see this narrowing of the standard deviation here in the outcomes of these randomized benchmarking measurements, even when the best case is not necessarily any better, right? But the worst case has been brought to kind of parity with the best case. You can do this in much larger registers. This is a calculation, I want to emphasize, where what we're looking at is the ability to perform arbitrary pairwise interactions between ions in a 10-ion string. This is part of an IARPA project where 10 ions is a magic number for some of our quantum error correction protocols. What you look at here is how well can you perform a Momer-Sorensen entangling gate in a standard setting where you just park your laser and you pray. And then on the right, where you do a phase-modulated control solution, implementing a dynamically protected gate for each particular setting. Now, there's variability because the way the ions couple to the modes of motion changes for those of you who care. But what each pixel here represents is the effective gate fidelity achievable for some pair of ions, say 3 and 8 in that register. What you overall find is that you can push down the total error likelihood using these control protocols. You can also narrow the variance, right? So this is just another example of how control can be relevant, in this case for an experiment that's leading towards actually implementing quantum error correction codes. So the last kind of key point that's going to be the rest of the talk is what we have taken to calling virtualizing the errors, asking about correlations of the error. Now, there's a huge amount of work that goes into this. There's a great poster on the role of coherent or correlated errors in QEC in the poster session. There will be a number of talks about this. I think we all are comfortable with the fact that quantum error correction does not fundamentally break when your error models have correlation. But we also know that in general, resource requirements go up. The more correlated, the more coherent your errors are. And so we're going to look at what we can say about error correlations, again, in the context of using control solutions as a means here to change the correlations. And what, the takeaway point to lead with is that when you use these dynamic error correction or dynamic error suppression strategies at the physical layer, you modify the underlying error correlations and you make the errors much less coherent. You make the errors much more Markovian or IID in their appearance. And so how we measure this is what I'll tell you about. The key idea to start with is that noise correlations generally translate to error correlations. And you can have two different regimes where I'm just looking at a circuit in time. This happens to be a randomized benchmarking circuit, and thinking about what the noise could be like. The noise in this case has a really short correlation time. It randomly fluctuates between each gate and the implementation. Obviously, this is a contrived error model, but it's indicative of one limit of like delta correlations in the noise and then the errors. And the other is quasi-static, where you have the same value of whatever this noise process is over the entire sequence. This is what we're going to broadly look at, the two extremes of strongly correlated coherent errors or uncorrelated, what you might call Markovian in a hand-wavy way, IID type errors. So let's look at what happens. How is this manifested? We perform randomized benchmarking. This is a kind of standard randomized benchmarking plot. Survival probability is a function of the gate sequence length. What we're doing here is we're actually engineering errors so we can validate some of the math that I'll show you. And then we'll look at the native noise in the system thereafter. But the key thing is that each of these data points in this spread at a fixed circuit length or sequence length corresponds to a different randomization, right? And you see that when you have uncorrelated errors, those fast fluctuating things, you get some small, narrow range of outcomes around the mean, and that's why we like the mean error as a proxy for how well you're doing. But if you have strongly correlated or coherent errors, you get this enormous spread. So we're going to look at one slice, a fixed value of J, the circuit length, and we're going to look at that data set. We're going to turn it on its side and turn it into a histogram. So that's what this is, right? And you see this is the histogram of the achieved fidelity or return probability for all different randomizations in the randomized benchmarking protocol. When you have that uncorrelated noise, you end up with this approximately Gaussian distribution. If you have strongly correlated errors, you get this long tail broad distribution. And in some work that my PhD student Harrison Ball did, and then we validated in detail in a Nature Quantum Info paper, we looked at this distribution and showed analytically that it is always, in all cases, something known as a gamma distribution, which is known in the engineering literature in the physics of failure, with just these two different parameters that tell you if it's more Gaussian in nature or it's more of this kind of skewed log normal looking thing. The important thing here is that there are no free parameters in these traces. It's not a fit. We've just overlaid what the calculated distribution should be based on the kind of noise we have in our system. But now we want to look more specifically at the width of that distribution. We want to look at the width of that distribution as we average more and more, as we take each data point and keep averaging. And so we're going to look at this, and we're going to look at this value of the variance as a function of averaging. And what you see is that for the black data, the strongly correlated noise, again with engineered error, and this is all experiment, that the variance saturates at some high value. Now all this jitter and stuff, this is just us shuffling the data in different ways to make sure we don't have a systematic bias in how the variance scales as we average. The point is you get this cone that just narrows to a fixed value. However, if you have uncorrelated noise, you get 1/n type averaging. And you see that the variance gets narrower and narrower. So this distribution will get narrower and narrower as you average more and more. And that's a key signature of the presence or absence of correlations or coherence in the error model. When you have totally stochastic noise processes, you get something that scales like this. As you average more and more, it gets narrower, but that width stays finite as you implement or you add correlated noise. Now this is a continuous process. You can have noise with varying correlation lengths, and you can see that the way you saturate is going to vary in a kind of systematic fashion. Again, no free parameters. These are just calculations overlaid with the data sets, showing that as the block length of the noise scales from being less than a gate to the entire sequence, you have this systematic increase in the saturation point, the width of that variance. Now, how do you interpret this? If you're a metrologist, I think this will be a very familiar concept, because we see this kind of physics in clocks all the time. What's going on? Here's a contrived, just numeric example. I made some Gaussian noise. I've plotted Gaussian noise as a function of time, and then I applied a moving average filter. And the filter averages more and more as I go from the black data to the blue to the green to the red. And you see that as you average, your variance narrows, right? This works when you have a white noise process, when you have an uncorrelated noise process. I think everybody knows that, right? But you also know, if you're in the clock community or if you've touched on it, that your Allen variance, as you average more and more, eventually hits some floor and then gets worse, right? That comes from the 1/f noise spectrum. So how is that manifested? Take the same thing and add a linear drift. That's a correlation or a coherence in the noise. When you have that, you see that the standard deviation here in these distributions, it does get a little bit narrower, but it doesn't continue to narrow as you average because you're now dominated by that linear drift. So that's the simple interpretation of the difference we see in randomized benchmarking variance scaling with noise averaging. So now let's take those gates and let's replace them with their dynamically protected cousins, right, with the quantum firmware version, and do the same randomized benchmarking experiments and look at the same thing like variance. So what's going to happen? Well, here's the interesting thing to keep in mind. There's a lot of work that's been done by my team, by Lorenza, Viola, and others, looking at what is the role of these error-suppressing techniques when you have time-varying noise. And what we learned is that you can always express these things in terms of what are called filter functions. It's like the engineering version or the quantum version of like a Bode plot, the frequency domain susceptibility of your control. And what Lorenza did quite beautifully is show that you can express this at the operator level. So if you have some noise which has a known spectrum, and maybe that spectrum is 1 over f, like is very common in a real laboratory environment, when you apply a control that modulates the kind of evolution of your qubit state as you go from, say, the North Pole to the South Pole, you end up with an effective error spectrum at the operator level that looks like the overlap of that noise, which is colored 1 over f, and this filter, which is low frequency suppressing. If you have something that's low frequency dominated and you pass it through a filter that suppresses low frequency noise, you whiten the noise. And we all know that things with white noise spectra are uncorrelated, right? So we know already that the action of these controls is to filter the noise. So let's look at the data. What you are going to see on the left-hand side is exactly what you saw before, correlated versus uncorrelated. And what you're looking at on the right, the noise is always correlated, except I've replaced all the gates in the blue data with the dynamically protected cousin, and they scale like 1 over n approximately. So now the signature of error correlations looks as if the errors are uncorrelated. I'll just point out that we've done quite a lot of first principles analysis on this in order to understand how well these gates work in terms of suppressing error correlations. In this particular model, we show that a standard NMR style control gives you about a 50 times suppression in the error correlation. But as is also known, because the gates take more time, you get a general increase in the amount of uncorrelated noise, right? So these come from fitting these data to our model. And it's a nice validation using these engineered noise protocols of how well controls actually modify the correlation structure in the errors. But now let's go back to the experiment with no added noise, right? This was all about validation of the model, and things work pretty well with no free parameters. Here's an example where we do randomized benchmarking in our trap. This kind of fidelity, the randomized benchmarking error rate is something like 1.5 by 10 to the minus 5. So that's, 0.999985 fidelity, average fidelity. When we do this with standard gates, or we do it with BB1, which is another NMR style composite pulse, we actually get about the same value. Within experimental error, it's 1.5 by 10 to the minus 5, right? So we have not gotten a net benefit in terms of error probability because this gate does not seem to correct what's our dominant source of error. But if you look at the same variance scaling with averaging, just doing more and more averages, you see that the primitive gate shows some saturation, indicating that there is a correlation in the noise, but BB1 gives you this 1 over n type scaling, indicating that whatever your residual errors look like actually have a different correlation structure now. You can extend this from 1 qubit back to that 5 parallel qubit operation setting that we talked about where we have this microwave field gradient. And we see that as we go from the ion on which we calibrate everything over to the other one, 1, 2, 3, 4, 5, that the saturation point in this variance scaling goes up because we have more and more correlated error. We haven't calibrated well on the 5th ion because we've calibrated over here. But if we replace all the gates with their dynamically protected counterparts, we end up with this BB1 scaling, again like 1 over n, and the order in which you find the saturation point is just random. It's just scrambled between these gates. Again, indicative of the fact that the error model has been changed, is no longer strongly correlated. You can look also at the correlations in space between these errors. Now, this is a very simple proxy measure where we look at the Pearson correlation coefficient of the error norm magnitude, so the magnitude how much error you have. And you see that when you have primitive gates, you're up near unity across this 5-ion register. The diagonal is obviously 1 ion with itself, so that's always going to be high. But if you implement these dynamically corrected gates, you see that you can suppress errors in such a way that you also reduce the correlation. You're dominated now by the incoherent, by the uncorrelated or stochastic part of the noise, which is let through by these control solutions. So at this point, I'm pretty much done. I wanted to give you a little summary, right? So we talked about the key benefits of these quantum firmware or quantum control techniques and how they intersect with quantum error correction. Beyond the kind of standard reported thing, which is you can make your gates better, you can also make them more homogeneous in space and time, which is extremely important for quantum error correction in terms of worst case errors, also important in terms of algorithmic implementation and how one has to do compilation if you're thinking about nearer term devices without error correction. And this last bit that I spoke most about is the idea of changing error correlations. That even if you can do proofs that show that quantum error correction still works in the presence of correlated noise, you seem like you may get a benefit in terms of resource efficiency by kind of preconditioning, by virtualizing the error model to look more like what is conventionally assumed in a quantum error correction analysis for some asymptotic scaling. And in the future, we're looking at making sure that these various layers in the stack start to blur together more and more. So blurring beyond quantum error correction and firmware up to the compiler level and beyond, looking at co-designing quantum error correction and physical layer controls, and starting to study what happens in realistic devices when you get the benefits of, say, homogenization of errors in space or simplification of compilers associated with replacing all the gates with their dynamically protected alternatives. And last year, building error suppression at the compiler level using some tools that we've built that calculate these noise filter functions for multidimensional systems for well beyond qubits. And then just the last bit of advertising is we also like to really think about how you can take these control solutions and scale them up to medium and large scale solutions. This was an example. I'll just point you to this archive paper from my student, Riddhi Gupta, who looked at using techniques from autonomous vehicle robotic control in order to do automated adaptive scheduling of characterizing devices in large arrays. And there are some huge efficiency gains that come from this technique we call NMQA, noise mapping in quantum architectures, previously QSLAM, but that led a lot of people to think it was a quantum algorithm and they didn't understand why we could run it on near-term computers. Anyway, this is a really nice technique for implementing control at medium scales for physical layer or at physical layers in the architecture. So with that, I'll acknowledge Claire, Virginia, Riddhi, Alastair, and Cornelius, who've led a lot of this work in my academic team, the research team at Q-Control, Harrison, Michael Hush, and Andre, who did a lot of the Mulmer-Sørensen and the multidimensional filter functions. I'll thank you for your attention and tell you we're hiring like mad in both our Los Angeles office and in Sydney. We'll be hiring about 25 people in the next 12 to 18 months. So if you're interested, please get in touch. Thanks very much.
Thanks, Mike. Are there any questions out there?
You were talking a lot about the different types of gate adaptions you were doing. For the effects you were showing, how often do you have to be recalibrating the gate sequence on the fly? And if so, what's the sort of resource time cost of that? And how many do you get where you're just essentially using a standard control sequence? How far does that get you? I just wasn't clear at the speed you were going with the talk, where you needed to do that and where you don't.
Sure. So it's a great question about how often one has to recalibrate. I mean, here's an example where this is using a kind of textbook control solution from NMR called BB1, and you see that there's no recalibration over an 8.5 hour span. Obviously, you see that the jitter out here is a little bit worse than the jitter over here, but it's much more tightly bounded. We find that for re-optimizing the controls, both on our hardware and on things like cloud-based publicly available systems, 6 hours is a good time scale to do full re-optimization, and that's a kind of couple of minutes in kind of calibration or characterization time.
Other questions? Please wait for the microphone because it's being recorded.
Do you know what your dominant source of correlations are? Are they just coherent errors or something like 1/f noise or something else?
So when we're talking about a single ion randomized benchmarking case, there it looks like we have some residual sub-hertz level detunings, right? So we can calibrate our qubit transition to about a hertz, but beyond that it takes a very long time to do the measurement, obviously. And it looks like it's that detuning that dominates us. So we can get a little bit of a win, but that by using something like Corpse or something shorter that does dephasing noise suppression. But then you get a little bit of the higher frequency noise that comes in. And also, when you do these protocols, we see that nonlinearities in the response of the vector signal generator actually become as significant as what we've just combated. And so we're moving to a new microwave architecture that uses arbitrary waveform generators.
Okay, thank you.
Sure.
Any other questions? Oh, right next to you.
I have a question about the RB sort of experiment where you showed just single qubit RB and you sort of made using these pulses, made the correlated noise seem uncorrelated.
Yep.
Let's imagine the case where you had 2 qubits and let's say individual qubit errors are maybe uncorrelated, but you could have some 2 qubit correlated noise. Would you be able to do similar tricks on making the 2 qubit correlated noise, let's say, disappear?
Yeah, so we have not done the same kind of lengthy investigation, but we have seen that, for instance, when you have a 2 qubit Mulmer-Sørensen gate and you have some trap frequency noise, that means that both ions will suffer a net error, that when you apply these error suppressing protocols, they also have a filter function that we can calculate using our tools. They also suppress the low frequency noise and whiten the 1/f type spectrum of trap frequency fluctuations, and one expects exactly the same thing. There will certainly be limits in which you can't get rid of it, but in the experiments we've done, we do see the same kind of effects.
Thank you.
Any other questions? Right here.
How fast are your 1 or 2 qubit gates compared to the textbook gates?
So there is kind of a empirical speed limit that one finds when one tries to do robust control, so that is building noise resilience. For canceling a single axis of noise, the fastest we can go is about 2.5 times the primitive gate operation. If you want to cancel both noise sources, control like over-rotation and dephasing, that limit is about 5 times the gate. Compared to something like C and BB, Corpse in BB1 or C and SK, those gate times are like 16 or 20 times the primitive, so you get factors of 4 or 5 improvement. And Ed Barnes's team has done a lot of work on kind of provable limits of the speed limit for robust control, and they also get values about 5 times as the limit for multi-axis noise suppression.
Any other questions? And I'll ask one final question. Could you pull up one of the slides with the software stack that you got there, with the firmware, et cetera? Yeah, so sometimes this interface between quantum error correction and quantum firmware, at least from the error correction side, gets boiled down to one number, like the probability of error of a gate or something like that. But of course, that's very artificial. It's much more subtle than that. Really, there's a whole syndrome extraction circuit that you have to worry about, and many things can go wrong in a circuit. And currently, my understanding is that the targets of quantum control really focus on this one number, the gate. Let's make the one gate really good, and if we can do that, then everything should work out. What's the state of the art for doing robust control, not on just gates, but on circuits, sort of expanding on this earlier question? Or maybe to put it more succinctly, how big of a quantum circuit do you think firmware could attack before you say it's just too hard to optimize or come up with a robust control solution for a circuit of a certain size?
Yep. Okay. So the first thing I'll say is that the nature of this talk was about trying to expand the metrics that we use to describe this interface to things like homogenization in space and time, or what is the effective error spectrum that gets experienced beyond just like P. What is the probability of error?
It's still one
And then,
gate, though.
that's right. That's right. And so when it comes to these larger things, I think the nicest work that I've seen on this recently comes from Fred Chong and Dave Schuster, where they use optimal control. It's a slightly different thing, but they're looking at the compiler level, breaking down circuits into kind of blocks where you can use optimal control to do that block instead of decomposing everything into X's and Z's and H's, the universal gate set. Our tools efficiently efficiently allow optimizations of complicated circuits. We've done it easily on about like 7 Q-trits, right? So kind of 21 dimensions in that case. It just gets slow in terms of the optimizers beyond that, but we can throw cloud resources and GPUs at it. But it certainly seems like if you think about blocks of, let's just say, a dozen interacting qubits or Q-trits with spectator levels, things like that, it's totally possible to do robust optimization of a compiled circuit, right? Where you can build in echo-like physics at the compiler level instead of thinking about everything in terms of individual gates.
Thanks. Let's all thank Mike one more time.